So I think everybody came back more or less. And we're going to have our next speaker now, Klaus Mosegaard, who is from the University of Copenhagen and the Niels Bohr Institute. And he will talk about dimensionality. Thank you.
Thank you. Thanks for inviting me. I'm very happy to be here. The title of my talk is Facing the Curse of Dimensionality. If you think this sounds like a space odyssey, it's not a coincidence, because this is probably going to be the closest you can ever come to a science fiction version of a talk about inverse problems. There will be, I guarantee there will be no real data. I will be talking about algorithms that hardly exist, and some of them may never exist actually. So there's certainly a challenge here for you, who are the future of seismology. So my talk will kind of connect to something we have talked a lot about, and that is computability. How do you actually make your inverse problems solver work when you have a lot of unknowns? And so this is so I will just with 2 slides just remind you of the big problem here, which we heard about already yesterday. And this is the use of sampling algorithms to do probabilistic inversion. And as you remember, the whole idea is that we have some probability distribution or probability density in some space of maybe a high dimension here, 2 dimensions. And then we have an algorithm that is miraculously able to generate points or realizations in that space that are with a density proportional to the distribution. So you can see here I've tried to put in some points which have a density approximately equal to the distribution. And here you should remember one important thing. This is very nice for a textbook, this figure here, but the reality is that we don't know what the distribution is. We only have the points, and we hope that our very intelligent algorithm is actually able to do this. And it's very hard to see if it fails afterwards. But, well, that's in itself a problem. The problem I will be addressing here is more how can we generate such realizations in finite time? What are the perspectives for the future with this? Maybe before I go on, I should just say, how do you actually use these? Andreas has already talked about that you can use these realizations to compute integrals, averages of anything you want, and that is actually practically a very useful thing to do. Another thing you could do is to simply go primitive and just say, okay, let me just have a look at these guys. And I could do that like on Hollywood. I could just make a movie, and then you can just try to plot the realization after realization, and then take a look. And in that way, I could see what the variability, what the uncertainty is of the model I have computed here. I took some seismic reflection data of the kind that the oil companies have used, and just generate some impedance models and show the updates. You can see there's a little jump, and that's because I start over again. But you can see the little jumps. It's from realization to realization. One thing, by the way, that is good here, it's just a little side note, is that you can actually observe the possible correlations there. You can see that certain pixels are following each other. It's one of the things that is very hard to see from an integral. So it's just to remind you that there is one extra thing here. But that's actually not the topic of today. The topic is how difficult is it to obtain this sample? And this is a long story, of course, but I'm not going to talk 24 hours about it. I'm just going to try and convince you about a few facts. And the most important thing I want to convince you about is that completely crucial is what you already know about the distribution you are sampling. So when you try to sample a distribution in a model space, any pre-knowledge about this distribution is crucial. And I will show you a horrible and extreme example of this, so you never forget it, hopefully. So let me first try and show you something that is apparently easy, and this is to sample a Gaussian, something you would probably never do. I mean, why should you sample a Gaussian? But let's try anyway. You would expect that if you do it, it will be finished before dinner. But I'll show you that it's not that simple. Here we have a Gaussian. That Gaussian is a little elongated in one direction. Here it's drawn in 2D, but I will, because of the title of my talk, I will go to higher dimensions in a moment. I will try to sample with this one using a Monte Carlo, I like to call them MCMC or Markov chain Monte Carlo algorithms. I don't like so much all these names with Metropolis and Hamiltonian and stuff, because it's all Markov chain Monte Carlo, and they have different, they can be poorly made or well made, but it's just the same basic idea for all of them. So let's try and use it here, and let's be simple and do it the way that has been done for many years now. A very simple implementation. The implementation is that we are walking around in this space trying to sample the distribution, and in order to do that, you know very well now that we need a so-called proposal distribution. This little guy down here, it's telling me that when I am at some point in a space, I take this proposal and center it in my point, and then I decide, using that little proposal distribution, I decide where to go. So using that one will allow me to make a so-called random walk in this space, and when it is running the random walk, it will, in the long run, it will sample this distribution. That I can prove mathematically, but this is not the problem today. The problem today is how fast is it. So let's just try and see what happens. And this is really, I don't know if any of you have any health problems, because if you have that, I will ask you to leave the room now, because now I will show you really a shocker. In 2D, you can actually analytically calculate the expected number of steps, the expected number of attempts you need in order to have an accepted move. You know, this MCMC, it proceeds by suggesting a point and then it's rejected or accepted. In 2 dimensions, on average, it's about 2.5 iterations you need, provided that, I should say that, of course, it's very wise to tell you what the assumptions are. The assumption here is that the proposal distribution has a variance of 1, and the distribution I'm sampling has a covariance where in the diagonal you have the variance is a diagonal matrix, and it has a variance that is 1 over n, so it's 1, 1/2, 1/3, 1/4, and so on in the diagonal. It's just I promised you, it's completely made up all this, so it's a toy problem, right? So I'm sampling this one with in 2 dimensions, of course. We have 1 and 1/2 in the covariance matrix. So I'm trying that, and then I have to wait about 2.5 iterations to have an acceptance. In 10 dimensions, now we are in the, starting to get difficult. You need 6,318 iterations to have an accepted move. This is quite a lot, right? And in n equals 100, it's just, I think they call it astronomical. You can forget about it. It will never happen. You will never have anything accepted here. So we can safely conclude that a primitive MCMC algorithm is just of absolutely no use when you go beyond something like, I don't know, Andrew always say 20, and so I kind of consider, in a moment I will show a theorem which I will call Andrew's theorem, because it's basically showing that he's right. that when you go to that above it, when you approach 2030, you are out of business. That's the point. So let's see. This is probably the first thing you would do if I asked you to sample this Gaussian. Now I will show you an algorithm that does not exist and it will probably never materialize. But that algorithm is much better. It turns out that it's possible to calculate how efficient the best conceivable algorithm would be, despite the fact that we don't know what it is. That's very strange, right? I'll show you. So here we have another Gaussian. I put it in gray just because Gaussians are boring, you know, so I didn't want to put that in color. And a Gaussian like this is defined by some parameters. First of all, we have a mean vector or mean point, a mean value if you like, and it has n components in an n-dimensional space. And you also need a covariance matrix to define the shape of the guy here, and it has n times n plus 1 over 2 independent components. So, in other words, the family of these gray Gaussians is a manifold of this dimension here. I mean, if you have these numbers, you have the Gaussian. It's enough. This means that if you have an algorithm, I don't know what it is, what that algorithm is, but you have an algorithm that kind of tries that many points in space and does it in a not too stupid way, then you are able to completely calculate the shape of this guy here. So, and then you're basically done. You can actually sample infinitely fast almost after that. Because if you have a Gaussian that is known, you can just go on with specialized algorithm and just sample. So it's infinitely faster than the first one we looked at. What happened? What happened here was that we know it's a Gaussian. We know it's a Gaussian. The way I treated the first Gaussian, the one with the 10 to the power of 80 something, was by sampling it with an MCMC algorithm that did not know it was a Gaussian. It performed exactly the same way as if it had been any other distribution. And this is crucial. If it does not know it's a Gaussian, it's very hard to sample. If the algorithm knows, I'm sorry about this fluffy expression, if it is built into the algorithm that this is a Gaussian, then things change completely. And this is actually my main message today, and it will be underpin many other things I will say, is that knowledge about the distribution you are sampling makes a complete difference. And that's why if somebody tries to persuade you that it's easy or difficult to sample a Gaussian, you should just shake your head and say, you don't know what you're talking about. This is not the whole story. It depends on how much you know already. This is, of course, not only the case for Gaussians, it's the case for any distribution you want to sample. The more you know, the faster you can potentially do it. Of course, we can all do primitive algorithms, and we do that. So off-the-shelf algorithms, you know, that it's just applied and then go. But if you have information, you can use it. So here's the first conclusion. You need so many, I mean, n plus n times n plus 1 over 2 function evaluations to completely characterize a Gaussian, if you know it's a Gaussian, in n dimensions. This means also, here comes the science fiction into play. Consequently, the best conceivable algorithm needs that many function evaluations to produce an exact sample from the n-dimensional Gaussian. So I don't know, you can easily make that algorithm. Actually, in that case, it's not difficult to do. I haven't tried, it doesn't matter here, but how do I know that this is the best conceivable algorithm? I don't know if you have any idea how I know this is the best conceivable algorithm. The answer is that if you have less than this number, then you cannot fully determine the shape of the Gaussian. There are infinitely many shapes of the Gaussian that are consistent with less samples. This means that it's impossible with fewer samples to sample the Gaussian correctly. So you need that many, but if you have it and you use them in a wise way, you can actually very quickly sample the thing. There are some standard ways of doing that if you know the Gaussian. So, yeah, that was the first thing. So please remember this Gaussian thing, but of course I want to persuade you that, well, you know there are other things in the world than Gaussians. You have the impression when you read many books that there's only Gaussians, but there are actually other things. And let me just show you another thing. Here's another thing here. I admit that this was actually made in Mathematica by just adding a lot of Gaussians. So you can see I'm still a Gaussian addict, but I shouldn't have told you that. But this is this guy here is just a random distribution in 2D in this case, but it could be in as many dimensions as you want. And you can see it is smooth. That's quite obvious. And the smoothness is actually something that we very often assume for good reasons. We can kind of even be sure that it's smooth sometimes. For instance, if you have a seismic waveform inversion problem, you can show that the misfit function, if you use the usual distance measures, that will be, I mean, the Euclidean distance, that one will be smooth. So this is what we expect. And if it is not smooth, then many algorithms are really in trouble. Especially, of course, linearized algorithms that try to calculate gradients and stuff like that. They will really be in trouble. So the smoothness is a common, not only a common assumption, but also a common reality, so to speak. Let's imagine that we expand this distribution on some base functions. So we have some base functions in the space, and we just now make an expansion, and then I only use a limited, finite number of base functions, because then I know that, I mean, this is a way of expressing smoothness, at least if the base functions are smooth. Actually, if the base functions are not smooth, I can just kind of generalize the notion of smoothness and say it's defined like this. This is a smooth, oh my God. This is a smooth function. So if I have a distribution that can be expanded in this way, and I now sample it. So I have an algorithm. It doesn't even have to be an MCMC. It can be anything that just picks some points. And let's say I pick k points. Then I can simply evaluate the value of f in those points, and then I get the values sk. And now I get this expression here, which is actually a matrix equation. You can see that. I've written it down there. I don't know if you can see it on the expensive seats down there, but you can see that there's phi jk thing here, which is components of a matrix, and uj here is a vector component. So I can actually formulate this as a matrix equation. So at this matrix equation, I have a known F matrix because I know my base functions. I have a known components of S because it's my samples, and this U, which is the expansion coefficients, they are of course unknown, but hopefully I could try and solve this equation and find the expansion coefficients. If I could do that, I would know everything about this distribution. That would be nice. Now I can safely conclude that if F is singular, or, let me be more modest, F transposed F is singular, so you cannot use these squares, then I'm not able to solve the equations. So I cannot find my expansion coefficients. And this means that in that case, I will have incomplete knowledge about the surface. I'm sure you're now thinking, he's crazy, that guy. He doesn't only want to sample, he wants to know the entire shape of the distribution. It sounds completely crazy, right? But I will explain, of course, try to get out of this by explaining to you that if this guy is singular and we are not sure about what the shape is, this means that this distribution has infinite variability. It has infinitely many distributions that fit our sample values. So this bad news here means that there could be a peak somewhere that we have not seen. And this is really bad because this is what we fear. This is what keeps us awake during the night when we are samplers, is that we have been sampling and we have overlooked a peak somewhere, maybe with the truth, who knows? I mean, and this is mathematically very simple to see here, that if this is singular, I should probably put F transpose 2, but you know the message here, then we are not sure that things are right. Okay, in other words, so if the number of required base functions, well, let me now try to say one thing. This distribution here, in 2D, you could imagine, for instance, that the base functions you choose are the good old sines and cosines from old-fashioned Fourier transforms, right? And then you can see that if you go to n dimensions, or if you go to higher dimensions, the number of base functions you need will grow exponentially with the volume of the space, or with the dimension of the space. And when it grows exponentially with the dimension, it means that the number of the number of coefficients you need to find, they grow also exponentially. And this means that you need a number of samples that grow exponentially. So this is really bad news. I mean, I remember I tried to publish this at some point. I got a message from the editor, something like, does that mean that we should never do Monte Carlo anymore? That was kind of the answer, and not very technically interesting answer, but he was very deeply moved by this very negative thing here. So, and I would like to call this Andrew's theorem, because it shows that you are out of business. Because the exponential growth, you know, this is the worst thing you can imagine an algorithm. Well, exponential and worse. That is the worst thing you can imagine when an algorithm, the behavior of an algorithm, when you increase the number of dimensions. So, in other words, we need some help here. We need to if we just go on sampling here without anything else, then we are in trouble. We need some help. That's the point. And now you still remember this science fiction algorithm that was doing the Gaussian very quickly. So let's hope that there's some help that can come in here. So, but let me just show one more thing. I've added a couple of more figures here. Let me just see. You know, the help we need, as I have told you a couple of times, is more knowledge about the distribution. Here we already have some knowledge. I mean, we know something about the smoothness, right? I can assure you that if we use base functions that allowed much more oscillations, it would get worse, right? We need some knowledge, and that's why I switched in an extra couple of slides, because here we have, again, it's the same as before. I just showed before, it's just not as nice. But here again, you have a sampling of a complex distribution, in this case in 2D. And one of the things that makes this hard for a MCMC is that in a classical MCMC, the most primitive one is the one where you make a random walk where you take first a move in one axis direction and then another one, and then you just go parallel to the axis. It's very nice very easy to implement. So that's why it's preferred by many. The problem with this kind of random walk that goes along the axis here is, of course, that you get very often disappointed, right? So you go in a direction and the probability drops. Here it's not so bad in 2D, but if you go to high dimensions, then almost all the directions are bad. So very often you see a drop in probability, so you get a rejected move, and it's just you cannot get home before 5. So what to do? One thing you can do is this one, and this is what you have heard about earlier. Here you simply, well, not simply. Here you need to know the gradients. You need to know the slope of this thing, which is a lot of extra information. When you have the slope, you can actually adjust your steps so they go either parallel to the level curves or perpendicular, which is along the gradients. Still, it would be a MCMC. You try and go, and it will be rejected or accepted. But of course, the good news is that there is actually many directions. Now in 2D, it's boring. It's only one. But in high dimensions, there will be many directions that go along the level curves. And those in that direction, you will very often have accepted your move. So it's a very efficient algorithm. I will be a little bit nasty here and say this has nothing to do with Hamilton's equations. Nothing. But the Hamilton's calculation is a nice existing method where what you do is you take your space here and then you add another space of more dimensions called the momentum space. And then you have equations known from mechanics that allows you to move along these level curves, because that's what a system that preserves energy does. And sometimes you give it a kick and then it changes the level curve and then it moves happily along that one. And once you have done that calculation, you say, okay, let me just project my result back to the model space. Because if you have sampled the distribution in the combined space, then you have also sampled the distribution in the marginal, in the original model space, because it's a marginal distribution you easily get. So actually, this is it's again science fiction. Nobody have done this. I should probably have done it before I arrived, but it's just a gift for you. I think you need a gift, so you should try it. You would, of course, need that's probably the entire work you have to do, is to find out how do I best move along the level curves. You know, in high dimensions, in 1,000 dimensions, you would have one direction that goes along the gradient, and the rest will be, in general, along the level curves, right? So you have to, you can try and think about it. I haven't had time to think about this, but I guess this is a very efficient approach for an MCMC. I don't believe you need Hamilton's equations to do that. Okay. Now, nowadays, everybody's talking about machine learning. And one of the things, I'm not going to talk about that, don't worry. That will be tomorrow, I think. That's very nice. But there are some ideas there that I think we have to think about. And one is that sometimes, at least that's what they say, and I think it's actually true, sometimes the solutions we are looking for, they are essentially located in a lower dimensional manifold, maybe spread out a little bit. So you have here's a 2D space, and you have a 1D manifold there, and then you have a distribution that is kind of centered along that one. And so what you would like to do is essentially to sample this snake-like distribution. And it's also true that if you try to do that and you say, okay, this is a 2D space, or even worse, if it's a 1,000 dimensional space and you are looking for a snake of dimension 5, it can be pretty hard to hit that one. If you go on in the 1,000 dimensional space, you will almost never hit it. So it can be hard to find. But once you have found it, or maybe you know already from the beginning where to start, then you have to be able to navigate. You know, it's also part of science fiction, these advanced spacecrafts. They have some fancy navigation equipment. They have to navigate in 4-dimensional space with funny objects like black holes and so on nearby. So it's very important to think about the navigation. And here, the navigation is given, hopefully, you have a map of that snake. So you have a local coordinate system along the snake from which you can move. If you want to find a point, it's a little bit related to what we just saw. You want to find a point along the snake, you can just go in one direction. And if you want to see how broad it is, you can go perpendicular to this. And this, so you need a local coordinate system in order to really exploit this thing. So, and that actually turns out to be very interesting. And I can already warn you now that I will probably say something in a few minutes from now that will surprise you. So just wait. But so let's go back a step. Just to show what the technology of words, the draw option in Word can do. Here we have a space where we have something. I've invented a word here, a new word, space-filling distribution. I was so fascinated about the analogy to space travel. So space-filling distribution, that's a distribution like the one we saw with the bumpy one. It's one that has, it may be complicated in some sense, but it has non-zero probabilities everywhere. It's a non-snake, so to speak. In this distribution, it's easy to find acceptable models. I mean, if you are somewhere, you just jump somewhere, it doesn't matter, you will find another solution with a reasonable probability. It's not so difficult. But one thing is to find an acceptable model. Another thing is, of course, to sample the distribution. We just saw that. That was Andrew's theorem. It doesn't work when you go beyond 22 dimensions or whatever it is. So this is what we know about this guy. So it has high dimension. We don't like that because we saw it doesn't work when we try to sample it in a direct way. So, but fortunately, somebody tells us, or we discover, that the solutions, they are in a subspace. They are in a snake-like subspace. Here's a snake. Here's another snake. It's a little bit different, as you can see. This snake here, this lower dimensional subspace, it has a map. It has a local coordinate system, so it can move around in it. Very nice. I always know where to go. If I am in the snake and you ask me to go to another point in the snake, it's very easy. I just follow one of the arrows here. It's there. It's very easy. I can make a very efficient algorithm that can move around in this snake. And this means that I have really reduced the dimensionality, as we say. Maybe we should say I've reduced the degrees of freedom in that case, so I can manage it. It's a low dimensional subspace, and I can move around it, and I can basically forget about the surroundings because I have this map. But look at this one here. This one is bad news because this one does not have a map. And I will show you a concrete example, maybe violating a little bit. No, I'm not violating my real data assumption, but I will not show you any real data. But I will show you an example in a moment of this, and a geophysical example. And this is a lower dimensional subspace, as you can see, but it has no map. So there's no way, when you are somewhere in this one, there's no way you can easily tell where you continue. So if your algorithm has hit this snake, it will just have to look around in the high dimensional space to find out where the continuation is of this snake. So it doesn't help you. And this is, please note this is the shock. I'm sure most of you thought that if you reduce the dimensionality like this, then you are happy. But no, here you are not happy. Here you are happy, but not here. Because even if you have reduced the dimensionality, you don't know where to go next time. You don't know where to find the other points in the snake. You have to search in the high dimensional space to find it. So, in other words, let's go to high dimension here. That was very, very easy. Here you are still doing well because you can just forget about this high dimensional space. It's 1,000 dimensions, but here you have a one-dimensional subspace. You just walk around and forget about it. Here, every time you want to find a new space, a new point in this lower dimensional space, you have to look around in this high dimensional space to see where it is. This means that you are in a worse situation than you would have been if you just had to sample the high dimensional space. It's even worse. So this gospel about reducing the dimensionality, forget about it. It depends on if you have a map of this lower dimensional space or not. And then I know you have noticed that I said that I will talk about things that don't exist and so on. So I'll just show you an example of a lower dimensional space that is like this, I think. So let me try and explain. So here we have again this seismic problem. I showed you before some seismic reflection data, near vertical. Actually, it looks like quite flat layering. And here I'm trying to solve the inverse problem, but I use a prior. I constrain my solutions. And they are constrained in a very well-known but special way. It's known from geostatistics. These models here, they are realizations from a so-called multiple point algorithms. It's an algorithm that has basically learned the structure from a training image and then is able to generate new random models that look like the training image. And it's doing that with a very special strategy. The good thing is that the nice thing is that all the models that it produces, they look right. I mean, they kind of, if it's a training image look right, then this one also looks right. So it's kind of has the right layering and so on. And this is great because this means that you narrow in the solutions. I mean, if you can imagine how many pixels there are in this image. It's a huge space, very high dimensional space. But the space of these admissible layers, models, is much, much smaller, of course. It's much, let's call it lower dimensional. I don't know exactly how it looks. It could be fractal. It could have dimension 5.7 or something like that. I don't know. But the point is that once you have found one of them, it's not easy to find the next one. And it's even worse to find a next one that also fits the data. If this one fits the data within the error bars, and you ask the algorithm to generate a new one that also fits the data within the error bars, it will not happen. It will just destroy the good fit because it's just doing something here that has nothing to do with the data. You are actually in a low dimensional space, very low dimensional space, but it doesn't help you. This one that I have tried, I should say. It's not completely fiction because I was very interested in trying to use multiple point geostatistics to generate, to sample the prior. It would be very nice because they look so realistic, these models. But it actually failed because of the inefficiency. We have found ways of generating these very fast with neural networks, but even there, I mean, they are much, much faster, but it's still pretty tough to find something that is useful in this very high dimensional space. So we have a preliminary conclusion, and this is against the normal gospel, this one. A posterior, a distribution that is only non-zero close to a subspace, as the snake, described by local coordinates, is easy to sample. That is still valid. If you have this snake with coordinates, everything is fine. You have a smaller space dimension. A posterior that is only non-zero close to a subspace without local coordinates is difficult to sample. And that's probably an understatement. It's difficult. It's horrible to sample. And the worst thing is that the difficulty of this non-parametric snake grows with the dimension of the embedding space. So the bigger the surrounding space is, the worse this is. So you can see it's really complicated how the dimensionality and degrees of freedom are working here. Okay, yeah, after all these bad news and stuff. I'll try to say talk a little bit about how one can try to add information about the problem, so one can, in a good way, reduce the difficulty and the size, so it gets kind of lower dimensional or limits the solutions in a way that is practical. And we all know one way of going. We all know that very well. That's applying a prior. We know that. We have a prior. That prior can shrink the whole thing so it becomes manageable. And that's what we do every day, right? But that's a problem we all know also, that the prior will bias the solution. When you present your solution to someone, they will just shake and their head, say, what is your prior? I don't like your prior. And then you have to go back and find a new prior. It's very depressing. So is it possible to shrink the space somehow without applying a bias? It sounds like not possible, but let's try and have a look. I will show you a face. This is one of the guys who wrote the famous book by Landau and Lifshitz about theoretical physics. And this is a quotation from him. He said, most important part of doing physics is the knowledge of approximation. And I think you can acknowledge that. I could also have shown a picture of Feynman. I think he said something like that. He was a master of simplifying everything and then work it out approximately. So the question is, would it be possible to guide our sampling using approximate physics? Would that be possible? But in a way that will not spoil our solution, because, I mean, I think we all do approximate physics. I mean, what is ray calculations when you have the full wave field? It's an approximation. So we all know that, but we also know that it's not so good because it will kind of, sometimes it will bias our result, and we don't really want that. So approximations are good, but we would like still to do the correct calculations. So let me show you a possible approach. I'm not saying that the algorithm exists really. Well, actually, I'll show you a prototype calculation from that, but from the method. But it's still something that needs to be tried in many other problems. So let me show you something in color here. This is just the inverse problem again, illustrating the forward problem. To the left, you have the data space. You have some seismic data here, right? At this point, this is your measurement. And then on the right-hand side, you have many solutions that fit the data. There's also some circles around it. It illustrates noise around the data and prior tolerance around the models. So this is roughly the situation. And when we want to solve an inverse problem, of course, we want to go the other way. And so we want a good algorithm would take the data and then generate multiple solutions showing how many ways you can fit your data. That's very nice. Let us now make a phone call to Landau and ask him what he would do. And he would say, I don't know anything about this, but I would like to make a very simplified model of what is of your complicated seismic problem. And then I will solve it, 3 lines on the back of an envelope. I will solve the problem for you. So he will make an approximation. And it sounds ridiculous, but let him just do it. He likes it. So he will do this. He will take the data. He will do a back of the envelope calculation. And then he will arrive at a result which is for sure wrong, right? He will probably be satisfied because it's close enough and all this. But this is not the game we will play here. We have actually, paradoxically, in geoscience, we have some kind of aim. We want to do things right. And sometimes in theoretical physics, it's more like showing the principle. Here we want to do things right, but we are kind of happy that he has shown us a rough method. Now we say, okay, we can use your method, but only if you can tell us what the error is. He would probably not like that. But so can you tell us what the modelization error is of this? So we call it the modelization error. We have some habits of language. So what is the uncertainty, so to speak, of this one? So after a while, he comes up with a big circle there, says, this is my uncertainty. And you can see conveniently I made it so big that it contains the correct solution. So that's very nice. So so now the game will be the following. If we have an approximate solution, and we have the modelization error, and we assume or hope that everything is correct so that the real solutions, the solution we want to find, they are inside there, can we use this modelization error concept and to help sampling, make a Monte Carlo sampling, for instance, of the solutions. So let's see if we can do this. And the dream is to build approximate physics into the MCMC without bias. That's our dream. So we are not asking for prior information here. We're only asking for guidance, right? So let me show it in a different way. So here we have here we have the situation in a different way. We want to sample a posterior probability density. It's like this. But Landau, he was not in the mood to solve that. He just made a rough calculation back of the envelope, and he came up with an approximation to the posterior. Because it was an easy calculation, he could very easily work it out. And if that posterior is kind of similar to this one, what does that mean, to be similar in this case? It means that, because, you know, as we have talked a lot about, the nasty thing about this distribution is that it's bumpy, and we are afraid of not being able to jump from one peak to the other. Within Monte Carlo, it will be stuck and all this stuff. So the point is that some of the major peaks in the posterior, they are hopefully also present in the approximation. So to put it in a different words, the hope here is that the approximation is an approximation, but it has kind of the same structure, physical structure as the real one, as the exact one. So hopefully it will, although it's not precise, it will hopefully have the peaks roughly in the same place. Now the idea is very simple. I think you have already guessed it because you are clever here. So you already guessed it. If I can propose in my Monte Carlo, I can propose jumps or propose models according to the approximation, and then accept it according to the posterior. Then I would be able to more quickly jump from one peak to the other. And but I've been talking a lot about not biasing the solution. How do I avoid that? I avoid that by using good old Hastings method, which means that you do I don't know if you can see it on the expensive seats down there, but I will tell you that when you do your metropolis or your MCMC decision, which is you take the ratio of the probabilities where you are and where you go, then you can, if you have a proposal that is kind of not so nice, it doesn't matter because you can just compensate for the lack of niceness of the proposal. For instance, if it is not symmetric, it's one of the things that is very common, that proposals should be symmetric. If it's not symmetric, you just multiply with the ratio of the proposal for going one way and going the opposite way. This is the Hastings method. This means that the proposal, in my case here, this guy will be my proposal. Although this proposal does not satisfy any nice properties, it doesn't matter, because I can just compensate with my Hastings ratio down here. And this means that this proposal, the structure of the proposal, will disappear from the sampling in the long run. You know, everything with MCMC is asymptotically, of course. So in the long run, there will be no imprint of the proposal because it is taken out by the Hastings ratio. You know, it reminds me, I mean, if I'm searching for something, now I don't know the terrain here very well, but I would like to sample the terrain. We have been out on a walk today. It was a little sampling. It was not random, but it was quite directed. But if I want to sample this area, and I have a clear opinion about where I want to be, and then I could, of course, just start randomly walking around. But if one of you know the area, you could help me by pointing and say, try and go over there and see if you find what you want. Then you will be my proposal distribution, right? So I will walk there, and then I would take a look and say, oh my God, you have completely misunderstood me. This is not my interest. I go back again. And then I apply the Hastings ratio. So forget about that one. So I remove your bias. And then I go back and ask you again. But you are quite clever. You have actually seen a map of the area to say, okay, you don't like that. Try this one over there then. And then although I reject a lot of your proposals, I still you guide me so I don't go the wrong places. It takes a long time before you do the stupid things because you are trying to help me. And this is the same thing that happens here. This thing here is guiding our walk. And if it fails, if it asks you to jump to a place that is not relevant or not good, it will be compensated for. So in this way, we can apply what you might call it a silent prior, maybe. I don't know. If that could be a prior that helps you, but it doesn't make any imprint on the solution. Let's take an example, take a look at and see if we can make it work. So here's one. Of course it does, otherwise I will not show you. So here we have a series of horizontal layers, and the acoustic impedance of the layers there. Actually, there's 1,000 samples here. So this is a 1,000 dimensional model. And I would like to sample that 1,000 dimensional space with an MCMC algorithm. I'm crazy. I just want to do that. And I know it will not work if I just start sampling. It will go completely bananas. So I will try to be guided by approximate physics. So I call Landau again and said, what can you do to help me today? And he would say, this one I would never do this, make a full waveform data. It's too complicated. No, I'll just make you a very rough approximation. So that's what he does. First, I have, of course, calculated, here's 5 copies of the seismogram from a vertical wave going down. It's just the inverse scattering problem, a very famous old inverse problem that has been seen in the literature for many years. So here are 5 copies of the wave you receive at the surface if you inject a spike, a delta function wave, and you just receive all the reflections. So it contains everything, including echoes and stuff. But Landau, he doesn't care. He says, okay, here's your data. But I have another suggestion, much easier. Here again is your data, your calculators. But I have here a much simpler way. That is the convolution model that is used everywhere in reflection seismic. So it's actually a linear model. Beware, this is not a linearization. It's very important. But I happen to use a linear model in this case because it's simple. It's very quick. And so he gives me this one, say, this is almost good, isn't it? I mean, it almost looks right. And of course, I'm a little bit nasty, so I subtract them so you can see that they are not the same. Because all the echoes that is in the first one, they are not in the second one, so you will have the echoes out here, the echoes that he left out. But I say, okay, fine, I'll try that. I use your simple model. So let's try and see what we can do. So here, on the left, you have again the acoustic impedance, which I call the true acoustic impedance. But here to the right is the acoustic impedance I have calculated by taking Landau's model and done a linear inversion in the good old style, a linear inversion of the data. I get this. And it looks pretty good. But of course, there are some problems. In the beginning, it's almost identical because you're not fighting with echoes up here. But after the strong reflections, then you have a lot of echoes, and then it kind of doesn't work so well down here. So there's a bigger error in this zone and downwards. So there are some problems. But still, I mean, this is Landau's suggestion, his best bet. but it's obviously not correct. So, of course, I will follow the plan and I ask him, what is your error? How big is your error? And he says, I don't know. You figure out yourself. I'm out of here. So I'm left with his solution, and I have to calculate the error. It's not so difficult because I just subtract the two, of course. But it's not so nice to have a method where you have to subtract your result with the truth from the truth, right? Because you don't know what the solution is, so it's not so nice. You cannot. Here we know what the result should be, but in real world you would not be able to subtract them. So we have to make some tricks to find the error, the modelization error, even when we don't have the true one. And here we make a trick which can be used for, I believe, any problem. A very important trick. Actually, it's partly stolen from image analysis, where they, in some other context, use this. What you do is you say, okay, I don't know what the true model is, but why don't I play a little game? I play the game that this is the true model. And Landau's model is the right one. And then I generate full waveform data from that. So I get some kind of true data from that. And then I use Landau's simplified method to invert that one. So I get a kind of a second order linear approximation to that. And then I can subtract that from this one. So I kind of shift the problem from being a comparison of the true with the approximation to comparing the approximation with a second order approximation. And then I can subtract the two and see what the error is. And if this one is close enough to the real one, which I believe it is, then I can hope that my modelization error I got from this little trick will actually work. And in this, of course, otherwise I wouldn't have shown you, it works in this case. So here you have the real modelization error. It's quite big here, where you have the big reflectors. And here's the modelization error estimated from the using the trick. And this, so now I'm kind of happy, except that I haven't told you how I will use this modelization error. But let me tell you how I will use it. What I will do is I will say, okay, now I'm going to do Monte Carlo to sample my problem. And I will now make I'll now propose, I have to propose models in my Monte Carlo. I will do it in a way that is, I will start in Landau's model. It will probably fit the data reasonably well. And then I will deviate from his model, but the deviation from his model will be equal to the modelization error. So at the top here, it will be that big. Down here, down here there will be a big deviation, and down here will be not so much deviation. So I kind of use Landau's model and the estimated modelization error to tell how to jump around. And so this is I mean, it was this one. Where is it? Oh my God, have I gone so far? Here we are. So here's a Landau's model, right? And what I've just estimated is this modelization error. So now I'll jump around here, right, and do the sampling. This may not look like a big help, but if you have a 1,000 dimensional space, imagine you narrow in the space with just a factor of 2, then the volume will be 0.5 to the power of 1,000 smaller. That's a lot, right? So it's a dramatic change. Let's go forward here. So what I have done now, I have defined the proposal. Actually, I just to test it, let's be as stupid as possible. We take Landau's model, we make a Gaussian in 1,000 dimension with standard deviations given by this thing here. So we actually have this circle around Gauss. The approximate model will be a Gaussian distribution with these standard deviations. And then I use that Gaussian to propose models when I sample. And remember, I take it out with the Hastings trick. So it will not bias my solution, but it will direct my sampling. So I will not get a posterior that is multiplied by a Gaussian. I will get a posterior that in the long run will not be influenced by the Gaussian. I'm honest to say, in the long run, in the short run, it will probably be influenced, but when you continue sampling, it will be eliminated. So here's the result. I hope you can see it. Here you have the three seismograms, the correct one, the approximate one, and the error. Here you have a true model, which we happen to know in this study. I promised you no real data here. And here we have the solution, the solution from the linear method. It's of course quite smooth. Here we have the true modelization error. So it's basically the error of my, it's the error of this solution here compared to the true one, right? And here's the estimated modelization error, which is quite good in this case. And then we start sampling. We sample this 1,000 dimensional space with an MCMC. And here's one realization. And here's the median of all the solutions. And if you compare the median here with the true solution, you can see that although we are only basically interested mostly in speed here, the quality of the solution is quite good too. So let's take a look as the final thing of the speed. And the speed here is here. Here you have the misfit. It's actually I'm trying to show the convergence in the stochastic sense, how the relaxation of the sampling. You want a sampler that has basically a constant deviation as a function of iteration when it's sampling correctly. And here you have the MCMC without this mechanism. It's just a classical MCMC. It starts with a big misfit, and then it flattens out slowly. You see after 2,000 iterations, it's not yet flattened, but it's on its way. It should probably out there. It would probably come down to close to zero. And here you have the curve for the one that is guided by Landau's model. First, it drops like a piano from 6th floor. And the reason is, of course, that you start with the Landau's model. Landau's model is bad, but it's not that bad. So immediately you have a gain. I'm sure you have all tried to do that kind of things. If you do my MCMC, you're so fed up with the slow performance, so you just try to feed in some good solution in the beginning. So that's not very surprising. But it's dropping, and then you start sampling using this guided by the Landau model and the modelization error, and then it flattens out here and equilibrates. And the point is that it's very hard to calculate, but it's just a rough thing. It's between 1 and 10,000 faster equilibration in this way. Let me give you a couple of disclaimers here while I'm stopping. First of all, the drawbacks of MCMC is not gone. I mean, you can still get trapped in local maxima for the distribution because the equilibration, the convergence is something that happens as the number of iterations goes to infinity. It's asymptotic. It's working properly asymptotically. So in that sense, there's no miracle, you can say. So, but what happens is that you are quickly directed to the places where you have high probability. So although it has probably not completely sampled completely correctly out here, it has still visited a lot of high probability areas, and but the opposite may be not. But it may not be the case for the MCMC, which may be stuck in the first maximum at C. So it helps you especially in the beginning, so we quite quickly get good results. But of course, there's still no guarantee on not being trapped. So that's for sure. So yeah, so I think I will not torture you anymore with these non-existing algorithms, but there are other applications. I have a very controversial and strange example. I just showed you one slide with a 1 million parameter problem. You can read about that in the literature, but it's just to take things to the extreme. when you do science fiction, you have full freedom to do crazy things. So thank you for your attention.